Hi, I am Hongjun Kim. I will talk about computer-directed software error resilience for lightweight GPU register file protection. This is a collaborated work with my colleague Jing Liu and Dr. Abdulmajid and Dr. Zheng and my advisor Dr. Lee. Nowadays, a majority of supercomputers equip large number of GPUs to accelerate power computations. These GPUs designed for HPC have already adopted hardware support for soft error resilience. When a high-energy particle strikes the circuit, data residing in the GPU can be corrupted. Such data corruptions are critical for HPC applications with immense parallel threads because a single data corruption can result in hours or even days of computation wasted without an error resilience scheme. A GPU consists of many streaming multiprocessors, and each of these SM owns a group of execution cores and thousands of registers. GPUs rely on a huge register file to store a massive number of parallel thread contexts. Conventionally, the register file is protected from soft error using ECC. However, the problem is that the ECC not only imposes significant hardware costs with additional parity bits, but also consumes substantially more energy. To replace ECCs in GPU register files, we propose Penny, a lightweight compiler-directed resilience scheme that combines error-detecting code with idempotent recovery. For ECC, errors in register can be corrected using the additional parity bits. However, this error correction requires a high bit redundancy. Instead, Penny uses much inexpensive error-detecting code to detect errors, and the error is corrected by re-executing the current idempotent region, which leads to much lower cost. A region of code is idempotent if it can be re-executed many times and still result in the same output as the original execution. At any point in the region, the execution can be restarted. Because the error detection code only requires detecting register corruptions and does not require redundant information for recovery, the hardware cost is significantly lower compared to ECC. To recover from a single bit error, every 32-bit register should be encoded with an additional 7-bit of parity with SecDec encoding. The number in the tuple implies that 39 bits are required to encode 32 bits of data. Our simulation results show that ECC encoding imposes 22% area overhead to the register file. On the other hand, for single-bit error detection, Penny only needs a single parity bit for every 32-bit data, reducing the overhead significantly to 3%. This savings on overhead becomes large for multi-bit error protection, which is gaining more importance due to advances in semiconductor scaling and near-threshold voltage computing. Other than reducing the hardware cost for same resilience, the system designer can also use Penny to achieve much stronger resilience with the same coding scheme. Note that SecDec can detect up to 3 bits of data corruption but only safely correct 1-bit errors. Our simulation result also shows that savings on the excess energy and leakage power are highly correlated with these area savings. Penny's idempotent recovery is based on previous recovery scheme named BALT. BALT's model is good fit for Penny because the eager checkpointing model can safely recover from register corruption, although there should be some modification for GPU. I will briefly explain how BALT's recovery model works. First, all memory antidependence is split by region boundaries. If these memory antidependence resides in the same region, the code cannot be safely re-executed. So all antidependents are cut by region boundaries to place the dependent load and store into separate regions. Now all register updates that is live out of current region and used in following regions are all checkpointed right after the update. For example, these R1 values are live out of the region and used in 2 following regions. So the updated value is checkpointed after the load. This is called eager checkpointing. Similarly, these updates are also checkpointed. The saved register values are used to restore the live in register values for idempotent re-execution. For example, if an error occurs here, the execution can safely return to the beginning of the region after restoring these 2 live in values of the region from checkpoint storage. But simply applying the idempotent recovery is not enough to achieve our goals. Here are the main issues we have to deal with. First, we need to show that using EDC with idempotency can still guarantee safe recovery. Second, we needed to prevent checkpoints being overwritten before the use for recovery. Lastly, because the stores are in the critical path of execution, checkpoint instructions can cost much higher overhead compared to CPU. First problem is to ensure safe recovery when combining EDC with idempotent recovery. Previous idempotent schemes require the errors to be detected within the same region where they occur. This imposes high costs of implementing the detector in such a short detection latency. On the contrary, Penny does not require such a restriction. EDC detects register corruptions when they are accessed which can be in a far later region from where the error has occurred. The recovery scheme only has to re-execute the current region where the error is found. We provide a proof why this is still safe. One good quality of using EDC is that errors are never propagated before detection. In this example, multiple registers are corrupted, which are originating from multiple events. A register corruption is first detected in a later region. At this point, we can be sure that no corrupted values have been propagated to other storage. If it had been accessed by another instruction for propagation, it should have been detected by EDC earlier. But since this contradicts the fact that original corruption was the first to be detected, it is guaranteed that register corruption has not yet been propagated. Now let's consider the state where a parity error is detected and the execution is about to jump back to the beginning of the region. Due to the previous proof, the corrupted values would have never been propagated to the memory and checkpoint, and with the ECC protection, both storages are intact from soft errors. Therefore, the live and register values can be safely recovered from the checkpoints and the idempotency of the execution can be guaranteed. The second challenge is to prevent checkpointed values from being overwritten before it is used for recovery. In this example, both updates of R1 in the first and the second region are checkpointed due to its use in the following regions. Let's consider a case where an error is detected after the second checkpoint. To re-execute the second region, live-in values of R1 from the first region is required. But this value has been overwritten by the second checkpoint, so the execution cannot be correctly recovered. For previous idempotent schemes, checkpoint stores are buffered by the CPU store queue and delayed until the end of the region to prevent this. Because GPUs does not have store queues, we propose a software-based technique. So Penny uses 2 storage space for checkpoints and alternates the storage for each region. Assigning storage to each checkpoint can be seen as a coloring problem, and coloring conflicts may happen. For the left execution pass in this example, the R1's checkpoint storage on basic block 4 has to be labeled K0 in order not to overwrite the previous checkpoint. But for the right pass, it has to be K1. In such cases, we insert adjustment code at the convergence point to unify the coloring state. The last problem is the high overhead of store instructions that are added for checkpointing. Since GPU does not have store queues, stores are on the critical path. So for the stores not hidden by the context switching, they commonly impose a significant overhead. Among the various optimizations we suggest in the paper, today I only explain 2 of them: bimodal checkpoint placement and optimal checkpoint pruning. First one is bimodal checkpoint placement. We found that restriction of previous eager checkpointing can be relaxed, so the checkpoint can be safely delayed until the end of region. This optimization focuses on moving expensive checkpoints in the loop to the outside of it. Left side is an example program, and the right diagram presents the relation between last update points and region boundaries. Last update points are the points where the live out register values are lastly updated, and each of them is presented as a node in the upper side. And region boundaries are placed on the lower side. To give a higher cost for checkpoints in loop, we weight the cost of each node as 2 to the d, where d is the depth of the loop where they are placed. Updated value at L1 is live out at boundary RB1 and RB2, so we connect them with edges. Similarly, we connect rest of the nodes. Now let's see the path between L1 and RB1. Rather than considering all points in this path, bimodal placement only chooses between placing the checkpoint right after the last update or right before the region end. Here we can select either node on each side of the edge. Let's select L1 and place the checkpoint there. Then we don't have to consider the highlighted path anymore, so the edges in the graph can be deleted. Since we have placed a checkpoint on L1, the edge between L1 and RB2 can be also deleted. Now let's select RB3 and delete the connected edges, and do the same to the RB1. So this final result tells you that by placing checkpoints at these 3 points, live out register value for all execution passes are safely checkpointed. We estimate cost of a solution by adding up the cost of all selected checkpoints. But note that by greedily choosing the cheapest node for each step will not necessarily yield an optimal solution. Finding a minimal solution in this graph is called a vertex cover problem. If the graph meets specific conditions, such as in our case, Koenig's theorem can be used to solve the problem in a polynomial time. Another important optimization is checkpoint pruning. We provide an optimal pruning algorithm that largely improves the optimization quality from the pruning algorithm suggested by Bolt. If a checkpointed value can be recomputed from other values at recovery, it can be pruned. In this example, a checkpointed value of R3 from region 1 is required for recovery of the region 2. However, rather than restoring the value from the checkpoint, we can execute this code called recovery slice and recompute the correct value of R3. So the checkpoint instruction can be safely deleted. Previously, Bolt has shown what conditions the compiler needs to verify to safely prune a checkpoint. We call the process of checking the eligibility of pruning a checkpoint verification, and use CV to represent the checkpoint being verified. The verification process follows the data and control dependencies recursively starting from the checkpointed value. Here, the R1's value comes from two different passes, so we also add the branch predicates in the recursive tracking. The tracking is done recursively and stops at a point other than register values, such as constants, memory loads, or when cyclic dependence is found. Constant values can be safely restored at any time. If a cyclic dependence is found in tracking, we assume it is not safe. For values loaded from memory, we have to consider if the value is still live until the recovery time. If all dependent values are safely reconstructible, CV can be pruned. However, even in case some of the dependents are unsafe for reconstruction, CV can be still pruned in case required values can be restored from other checkpoints. To use memory values or other checkpoint values for reconstruction, it has to be checked that if the value is still available at recovery. Here, R2's value at region 2 is used in region 3, so it must be checkpointed. We define a checkpoint's required range as the range that a checkpointed value must persist for a safe recovery. In this case, CV's required range extends until the end of region 3. The checkpoint value depends on R1's value that is loaded from memory address A. The memory value at A must not be overwritten until the end of CV's required range. So, the compiler checks if the stores in the path overwrite the load using alias analysis. In the right example, CV depends on an unsafe value loaded from memory, but it can still be pruned if CD's checkpointed value can be used on recovery. In this case, CD must be committed, and its value must not be overwritten until end of the CV's required range. If checkpoints such as COs overwrite CD, it is unsafe to prune CV. But the naive pruning algorithm Bolt uses for applying the pruning criteria is inefficient in that it still misses to prune large number of possibly prunable checkpoints. If we present pruned checkpoints as 1 and unpruned checkpoints as 0, the pruning solution of n checkpoints can be presented with a n-bit string. Bolt needs to verify n checkpoints for each solution, and there are 2 to the n possible solutions. Verification result of checkpoints cannot be used across pruning solutions because the verification depends on other checkpoints' pruning decision. Therefore, Bolt's naive algorithm requires exponential time to get an optimal solution. Since that is infeasible, it stops at the first valid solution it finds, compromising on a non-optimal solution. In contrast, Penny provides an algorithm to find the optimal solution in a reasonable time. Our algorithm uses 2 phases to achieve this. In the first phase, we collect the verification information without the preconceived decision of other checkpoints. So Penny only needs to analyze each checkpoint once. Using the collected information from the first phase, the second phase can infer which checkpoints pruning must be decided before others. This is called the decision dependence, and we can use this to order the checkpoints for verification. All this process can be done in a polynomial time except for the checkpoints with cyclic decision dependencies. For this limited portion of checkpoints, brute force search similar to the naive algorithm is used, but this is rarely found in the GPU applications. In the first phase, Penny traverses the data and control dependence similar to the verification process. The traversal continues until it reaches a point at which safeness for reconstruction can be decided. We mark S for values that can be safely reconstructed and U for unsafe ones. We can simplify the traversal graph to this. Once the terminal nodes are marked, their marking status are propagated back to the original checkpoint. If all terminal nodes are safe, the checkpoint is safely prunable. If one or more nodes are unsafe, it is unsafe to prune the original checkpoint. We call this a committed checkpoint. If there is another checkpoint in the propagation path of the unsafe status, the status is changed to masked. This is because, depending on the pruning decision of the intermediate checkpoint CD, the safeness can be changed. We mark the original checkpoint with D, deferred status. The second phase uses the markings from the first phase to make final pruning decisions. We first define decision dependence. CV has a decision dependence on another checkpoint, C0, if the decision of C0 must be made before CV. In the left example, CV can depend on the value of committed checkpoint CD for recomputation. In this case, the pruning status of C1 and C2 must be decided to verify if it overwrites CD. Therefore, both C1 and C2 must be included in the decision dependence of CV. Detailed algorithm on collecting decision dependence can be found in the paper. A decision dependence graph can be drawn like this to show all decision dependence between checkpoints in the code. The colored nodes have already assigned prunable or committed status after the first phase, and the uncolored ones are in deferred status. By topologically sorting the nodes in the graph, we can get an efficient order to finalize the decision of the remaining checkpoints. Now, Penny traverses the decision dependence graph in a reverse topological order to verify and finalize the pruning decision. For checkpoints with a cyclic dependence, which can be identified as a strongly connected component, we use a brute force search. In this way, we can finalize the decision of most of the checkpoints without repeating its verification. As I mentioned, the cyclic decision dependence between checkpoints are rare, and also the size of the group to apply brute force search becomes considerably smaller. Now here's the evaluation. We used the GPU Sim simulator to measure the performance of our implementation. The performance overhead of error-free execution of Penny is only about 3%, which is a drastic improvement from 67% of our unvarnished implementation of Ball for GPU. The major performance improvement comes from pruning. With Ball's basic pruning, 70% of the checkpoints are left unpruned in average, but our optimal pruning only leaves 25% remaining. The average execution overhead without pruning is 56%, and with basic pruning, it is dropped to 30%. Penny's optimal pruning further reduces the overhead to less than 6%. The simulation result of energy consumption on register files shows that Penny only consumes 7% more energy than execution without protection, while SecDec ECC consumes 22% more energy. In conclusion, Penny is the first compiler-directed technique to protect GPU register file without expensive ECC protection, and EDC can be well integrated with idempotent recovery. We provide various optimization, reducing the checkpoint override to 3%.